Okay, welcome to lecture. We're going to pick up here where we left off here on the last chapter, on the last day of lecture. So we're on chapter 17, equilibrium, which again is the last one, obviously, of the season here. We're almost done with it. So we're going to finish up this chapter and then obviously talk about some other stuff. And it was, like usual, if you do have questions, feel free to ask them in the box and we'll get to your questions and everything like that. Okay, so we are talking about equilibrium. We've been talking about equilibrium and we talked about a couple of things last time. Again, a reminder that when we talk about equilibrium, we are sort of focusing on a specific type of reaction, which are those reversible reactions. And as we talked about the last couple of times, these reversible reactions have a forward direction that goes from reactants to products. It has a reverse direction that goes from products back to reactants. And when we do reach chemical equilibrium, as we talked about a number of times the last couple of lectures, again, essentially what we mean when we do reach equilibrium, as we talked about, is not, again, that we have the same amount on both sides, but we're really talking about the rate. And it's the rate of the forward reaction will equal the rate of the reverse reaction. And that basically is what we mean when we reach equilibrium. So as we talked about, basically what that means is it's going kind of back and forth at the same rate. So pretty much when it does reach equilibrium, everybody sort of locks themselves into place at that point. And, you know, they're going to be able to sort of maintain their concentrations of where they're at. They're able to maintain, if we're talking about sort of pressures as well, the pressures of where they would be at that particular point. There is an expression that we can use to describe equilibrium, and that is capital K, and that's the equilibrium constant, which is essentially the concentration of the products divided by the concentration of the reactants. And remember as well, when we do this, there's a couple of things that don't make it into the K expression. We do not include things that are solid or liquid. That means that we typically only include things that have the aqueous symbol and the gas symbol into our equilibrium expression. Also important as well is we do use the coefficients. So if I just make up some here, and if we were to write the equilibrium expression for that top one with those made up coefficients, again, it would be our products, but we do use those coefficients as the exponents when we do it into the equilibrium expression, times our D, which is coefficient is 1. So again, we wouldn't put anything in terms of the exponent part. We would divide it by our A, which would be squared for the coefficient, and our B in this made up example, that would be cubed. So we do incorporate the coefficients from the balance equation into that products over reactants. Remember again that when we do talk about sort of this bracket, that means concentration, and it really means molarity, which is our moles per liter. You could also do this, as we talked a little bit about, we didn't get into a lot of it. You could also do it with pressures. If everybody's gases, you could actually use pressures and go into sort of this expression as well. That number or that value of K is a constant for a particular temperature. So as long as you keep the temperature the same, regardless of how much reactants you start with, regardless of how much products you start with, it will always be the same ratio of products to reactants when you calculate the equilibrium constant, as long as you don't basically change the temperature. If you do change the temperature, then the actual value of K will change. So again, as we talked about last time, you know, if you had a value of K for a reaction that was 20 at, say, 25 degrees Celsius, maybe that K value would be 60 at, say, 55 degrees Celsius. But if you stayed at 55 degrees Celsius, again, the K value will maintain its value, again, no matter how much products or reactants you start with in terms of that reaction. We can use it to determine whether or not K is large or small. Again, there's no units associated with K, so typically no units. But if K is large, again, what that means is we essentially will have more products than reactants when we reach equilibrium. And what that would essentially mean is that we would expect mainly products at equilibrium. And vice versa, if K is small, if you just think about it mathematically, that means we would have more reactants, bottom number larger than the top number, gives us a small number, and we would have more reactants at equilibrium. Remember, a large value for K is the big number of 1. And again, basically at 1, you would have equal numbers of products and reactants in terms of concentrations. But if you go above it, you have a little bit more products. Below it, you have a little bit more reactants. Then lastly, we sort of really sort of finished up with talking about what happens when we sort of mess up a system that's at equilibrium. So when we do have a system that's at equilibrium and we do something to that system at equilibrium, which is sometimes referred to as adding a stress to the system. And we talked about a number of different sort of stresses that you could add to a system. You could play with the concentration. You could play with the pressure or volume. You could play with the temperature. And again, the idea here is what is known as Le Chatelier's principle. And basically, you have a system that's at equilibrium. Then you do something to it to essentially mess it up. And the system itself wants to basically get back to equilibrium. So it wants to get back to that situation where the rate of the forward reaction will equal the rate of the reverse reaction. So in order to do that, usually 3 things will sort of happen. It will sometimes shift to the right, the equilibrium. It will sometimes shift to the left. And sometimes there will be no change, even though something happened. And when we talk about shifting to the right, what that essentially means is it will shift to the right. It will make more products. And by making more products, it will allow that system to once again hit a equilibrium condition where the rate of the forward reaction will equal the rate of the reverse reaction. If it shifts to the left, it means in order to get back to that equilibrium condition, you need to start making some more reactants. And there's some things that will happen that will cause no change. So when we talked about concentration, and basically we could either add or remove. And when we add concentration, it always shifts away from the side we added it to. So what that means, when you look at the balance equation, if you add reactants, it will shift to the product side. If you add products, it will shift to the reactant side. So if we look at the top equation there, if I added more A to that top equation, it would then shift to the right, away from A. So AA is a good way to remember that, add away. If I remove C in that equation that we see on the screen, that's on the right-hand side. So when we remove something, it actually goes towards the side we removed it from. So if I remove C from that reaction, it would cause the reaction to shift to the right towards the side of where C was removed. Same thing if I decided to remove B. If I remove B from that reaction, it would shift to the left-hand side because B is on the left-hand side of the equation. So as we talked about, there's no real kind of left and right in a beaker, but we sort of think of left and right in terms of the balanced equation. Is it shifting to the reactant side? Is it shifting to the product side? Now, when we talked about pressure and volume, that is related to gases, right? And again, it's sort of the Boyle's law relationship. As the pressure goes up, the volume goes down, and vice versa. As the pressure goes down, the volume will go up. So they're really tied together, and they are related to really, when you look at an equation, really just the gas molecules involved. And I guess we talked about last time, the best way to sort of look at it is, I think, in terms of volume. And that's usually a good way to know and look at these things. So if you understand that pressure volume relationship, that as one goes up, the other goes down, you can just look at the volume aspect of it and be able to probably get to the right answer. So when we think about volume, it's a very simple way to think about it is if you have a larger volume, you need more people to fill the room. So you need more gas molecules. So whatever shift that occurs that would cause a larger volume, And basically that would be caused by either a larger volume or a lower pressure. That would mean that you need more gas molecules. And that's really not a for sure left or right situation. That is solely based on the equation. And again, you would look in the equation and find everybody that has G's next to them, which means they're gases. And if they all had G's next to them, you essentially would just add up the coefficients and see how many gas molecules that you would have. So if one side said it had a total of 4 gas molecules, the other side had a total of 2 gas molecules. Again, just from adding the coefficients together for anything that has a G next to it, you'll know which way it would need to shift. In our particular example that I wrote on the screen there, if we made them all gases, we technically would have 5 gases on the left, 3 and 2, and we technically would have 5 gases on the right, 4 and 1. And that is a situation, one of the couple of situations that would actually cause a no change situation in that particular case. Again, because there's basically the same number of gas molecules on each side, which means there's really no larger side or smaller side in terms of gas molecules. And lastly, temperature is related to the same way as concentration, which means when we increase the temperature, we shift away. And when we decrease the temperature, we go towards it. And really what determines temperature is the type of reaction. So if it's exothermic, heat would be a product. And again, you would have a delta H value that's negative. And if it was this would be exothermic. Endothermic would be the opposite. You would have heat as a reactant, and the delta H would be positive. So if we have an exothermic reaction and we increase the temperature, it would be like adding to the right-hand side of the equation. And again, add would go away, so it actually would shift to the left-hand side. If we remove temperature or decrease the temperature of the exothermic reaction, it would be like removing the products, and it would go towards the product side in that case. So for temperature, it works the same way as concentration, but essentially you just need to figure out, is it exothermic? Is it endothermic? Any questions on any of that stuff that we talked about? Okay, so we're going to talk about some, just very sort of briefly, some calculations that basically involve equilibrium. And I'm not sure why they put it in this class, but we'll talk a little bit about it. It really is a lot of the calculations that you'll do when you go to 1B, but it kind of gives you, I guess, a preview maybe of it as well, so you have seen it, I suppose. So there's a couple of ways we could calculate K. Since K is the equilibrium constant, we can write the expression for K like we did in the middle of the screen, which is our products over reactants. And in order to actually get a number for K, we would need the equilibrium concentrations of everybody. So because it's an equilibrium constant, we would need the actual equilibrium values at equilibrium for each of those guys, the reactants and the products, to be able to put it in there. Now, if we don't know the equilibrium concentrations, but we're given maybe the initial concentrations, it does require a calculation to be done to sort of figure out the equilibrium concentrations. And we're going to see both of those things. So let's take a look maybe here. And this, I think we sort of just talked about. Again, if the equilibrium lies to the right, which means when we talk about right and left, reactants on the left-hand side, products on the right-hand side. So if it lies over here to the right-hand side, again, in terms of what you're doing is taking products over reactants, that means that we should have a lot of products. So the number on top should be large, number on the bottom would be small, and that would give us a large value of K, again, above 1. And vice versa, if it lied the opposite way, heading towards the reactant side here, that means that when we look at sort of just mathematically this calculation, the bottom side here would be larger, which means we're taking a smaller number divided by a larger number, and that should give us a small number for K. if we should expect mainly reactants at equilibrium. Remember, if K does equal 1, it basically means you have sort of an equal shot there of reactants and products, but basically the ratios will not be extremely sort of large. All right, so here if we have the K value for this reaction, and we want to calculate the equilibrium concentration of H2, given that the equilibrium concentrations of our other guys are given to us. The way we could do this is sort of like what it shows on the bottom, but you really would want to start with your equilibrium expression, which is going to be our product. So in this case, the concentration of HI, again, we do need to square it because of the number that's here. We're going to divide it by our concentration of H2, which the coefficient is 1, and the concentration of I2, which the coefficient is also 1. And that would equal 50 in this particular case. So what they gave us was the HI concentration, and they gave us the I2 concentration. So that is going to allow us to rearrange this and solve for H2. And if you do that, essentially what happens, you're going to multiply H2 to both sides and divide by 50. And if you multiply H2 to both sides and divide by the 50, you will end up with an expression that looks like this. And again, what we did is essentially multiply both sides by H2. These guys would cancel. And then we came back and divided both sides by 50. These guys would cancel. And then we ended up with where we're at right now. At this point, since we have all the information, as you can see below, we're just going to put it in. And that's going to give us on top 5 times 10 to the minus 1. We want to make sure we square it, divided by the 50, and divided by our I2, which is 1.5 times 10 to the minus 2. And obviously, we should hopefully get, I imagine, the number that they have boxed there, which will give us 3.3 to the minus 1. And just to verify, I'll punch it in real quick here. And that looks good. Looks like a winner, 0.3333, basically. 0.33. Now, because this is a concentration, you would put the N there for molarity. And again, obviously, this is the same as what they got here. So this demonstrates, again, in order to use K, these values here have to be the equilibrium concentrations to do so. And you can plug it in and obviously solve for it. Any questions on that there? Now, we could have all kinds of K values, and we talked a little bit about that at the beginning. There's Kc, which is basically the equilibrium constant for concentrations. There's Kp, which is the equilibrium constant for pressures. There's Kw that we saw when we talked about acid and bases, which is the water ionization constant. There's all kinds. There's Ka, Kb, Ksp, Kf. There's a lot of Ks. And again, if you take 1B, you will learn all those Ks in there. One type of K is what's known as Ksp, and Ksp is known as solubility product. That's what the SP stands for, solubility product. And it's basically the equilibrium for things that are typically insoluble. So if you remember those solubility rules, when you mix a couple of things, sometimes it will make a solid when you talk about an ionic compound. One example, for example, would be something like silver bromide. Silver bromide, based on the solubility rules, is insoluble. But just because something based off of the solubility rules are insoluble, it doesn't mean that it 100% stays as a solid. Everything to some degree has some sort of solubility. And even something like silver bromide will break apart a little, and it would break apart into silver ions and bromide ions. The amount it breaks apart may be super small, but there is some aspect of it that would allow it to basically break apart into those ions. And when we talk specifically about this type of equilibrium constant, which is the Ksp, that is pretty much how all the reactions are written. Solid on the left and ions on the right, basically. Your positive ion and your negative ion, which is aqueous. Now, if we were to write the Ksp expression for this, it would be our product, which is silver times the bromide. And like we talked about before, over our reactants, but on our reactant side, it's a solid. So it would not be included in the equilibrium constant here. So that's very sort of specific for this type of equilibrium, which is known as Ksp. It essentially will not have anything on the reactant side, which means the K values are essentially just the products. In normal equilibrium that maybe doesn't deal with sort of this type, you obviously will have some products and reactants like we did with this one. You know, the equilibrium expression had both guys in it, products and reactants. But in Ksp, it pretty much will only be the product side that's involved. So we would do the exact same thing, just like we would, because really a Ksp, a Kc, a Kp, a Ka, a Kb, they're all just equilibrium constants. They're all just typically products over reactants. This is bismuth 3 sulfide, which when it breaks apart, we get a couple of bismuths and 3 sulfides. So again, our reactant side would not be involved in the equilibrium expression because it is a solid. So we have 2 of these guys, which means we would take the concentration and square it. We have 3 of these guys, which means we would take the concentration of sulfide and also cube it in this particular case. So if we take a saturated solution of PbCl2 that's prepared by dissolving some salt in distilled water, and the concentration of lead-2 was determined to be 1.6 times 10 to the minus 2, what is the value of the Ksp? So again, if you sort of follow the solubility rules like we talked about, remember that things like chlorides, bromides, and iodides, they're soluble in everything. Except for 3 exceptions, silver, lead, and mercury 1. And in this particular exception here, we have lead involved. So again, where chloride is usually soluble, because this is one of those exceptions to the solubility rules, it would become insoluble. So PbCl2 would be a solid. It would break apart into lead with a +2 charge. And it would get 2 of the Cl minuses. So just like we do sort of like a net ionic equation and total ionic equation, when you break this apart, right, the 2 comes to the front and the guy gets his charge. We could actually write our equilibrium expression for this, which would be a Ksp. And again, it's going to be our product, which is our lead-2, times our chloride, which again, we do need to square it here because of that 2 that is there. In this case, they actually gave us the lead-2 concentration. So here we need to think about sort of what's going to happen to allow us to get to the chloride. And you can use a method which is what is referred to as an ice table, although you don't necessarily have to use it in this particular problem, but it may help us sort of visualize sort of what's going on. So to do an ice table, you basically start with your reaction. And ice means initial, C means change, and E means equilibrium. So ICE, ice table. So initially is pretty simple in this case. It's going to be 0 of each of these. And you could assume initially these are 0 unless you're told differently, like you had an initial amount. And we represent the change typically when you do an ice table as a variable, and we use X, for example. You take 1B, you'll use S, but you can use any letter you want, but we'll use X in this case. And X represents basically the change that's occurring in this reaction. So as we are going from reactants to products, and if you're not really given any other information, it is probably 98% of the time, maybe even 99% of the time, almost safe to assume that this reaction is heading in this direction, heading from the reactants to products. So what does that mean about sort of the reactant side and the product side? What that means about the reactant side and the product side in terms of the change is we would expect the reactants to get smaller as this reaction is progressing. So we represent the change on the reactant side as like minus X, for example. While we would represent the change on the product side as plus X. And the plus is because we should assume that this reaction is heading to the product side. And because it is, we should assume that we're making more products and the products should be increasing. So the change part of an ice table is represented usually by a letter. So we'll use X in this case. And typically speaking, the reactant side is where you have minuses of X's, and the product side is where you have plus X's. Now, it's also important as well, if you remember that basically when we have an equation, there's everybody's favorite thing, which is stoichiometry. And there's a certain mole to mole relationship between everybody in an equation. And when we do an ice table, we take that stoichiometry into account, or that mole to mole into account in the change part. And the way that we do that is pretty simple. The way that we figure out the mole to mole relationship is by looking at the coefficients in the balanced equation. So let's just say, for example, this guy was a 2 and this guy was a 3. When we would do the change part now, we would say minus 2x, 2 because of the coefficient. That takes care of the mole to mole relationship and all the stoichiometry. And then on the product side, we would say plus 3x, also for the coefficient, taking care of the stoichiometry, taking care of the mole to mole relationship, all sort of in one step. So it's important when you do sort of an ice table to include the coefficients with the change part, because if you don't, you technically will be doing the problem wrong because you will have the wrong mole to mole relationship. Question on that. So in this case, the change here on our reactant side would be minus. On our product side, this would be plus X. And on our others guy, this would be plus 2x. And again, the 2 comes from right here. Now, this brings us to equilibrium. And at equilibrium, we pretty much just bring everybody down. This would give us x, and this would give us 2x in this particular case. Now, you may be wondering yourself, what about the left-hand side of the table? How come we haven't been doing any numbers or anything sort of in this area here? And the reason we have not done really anything with that area is when we look at what's over there, we see a solid. And as we did at the very beginning here, that solid has no effect on the equilibrium, and it does not find its way into the equilibrium expression, which means we should not put any numbers on anything that's solid. You shouldn't put any numbers on anything that's a liquid. You pretty much, when you do an ice table, just really leave those guys alone. You just really deal with the aqueous guys. Any questions on that? If I did have something on the reactant side that was aqueous, so let's just suspend belief here for a second, and let's just say, hey, whatever this is over here, we'll pretend this guy is aqueous. Then you would do like a minus X and all that for it. But again, in this case, it's not aqueous, it's a solid, it's not going to participate. So you basically just leave it alone. Now, normally when you do an ice table at this point, what you would do is you would take your equilibrium expression, like we wrote at the beginning, which in this case, whoops, this case looks like that and this. And this typically would equal our Ksp value, or the K value, which in this particular problem, that's actually what we're trying to find. But usually what you do is you take these equilibrium guys and you basically plop them into the respective location here. So that technically would give us X times 2X squared would equal our K value, which again, in this case, is what we're looking for. Now, the good news is what they told us was at equilibrium, the lead concentration is this number, right? Which means if we follow down in our table, lead at equilibrium equals X, which means X equals 1.6 times 10 to the minus 2. And this X here, and this X here, and every single X in this table is essentially the same, which means we now have everything that we need to actually get to the Ksp. And we would take our 1.6 times 10 to the minus 2, like they did right below us. We would take 2 times X, basically. I'll do it this way. 2 times X, which is 2 times 1.6 times 10 to the minus 2. And that, by the way, is how they get to this number. And that will give us our Ksp value of 1.6 times 10 to the minus 5 in this particular case. So that is sort of how an ice table works. And the reason I said you don't necessarily have to use an ice table in this particular case if you understand molarity, and I'll show you that in just a second. But before that, question sort of on the ice table, how it sort of works. So the reason I said in this particular case, you don't necessarily need to use sort of an ice table is because if you remember something that we talked about when we were talking about solutions, for example, we know that PbCl2 breaks apart into Pb2 plus and 2 of the Cl minuses. What they did tell us was the concentration of this guy, which is 1.6 times 10 to the minus 2. And if you remember, if we look at the relationship between lead and chloride, it's a 1 to 2 relationship, which means you could figure out really just from the molarity, like we talked about, that you could just double the molarity of it. And that would get you right into the expression. And then you would be done with the problem. You don't necessarily have to do the ice table. The ice table sort of shows you where everything came from in this particular problem. Any questions on how we got any of those answers? Okay. Now, in a problem such as this, where the only thing you're given is like the Ksp value, then you definitely have to use an ice table. So if you're given only the K value, especially the Ksp value, you do have to use an ice table. And silver chloride, again, based on solubility rules, will be a solid. When it breaks apart, it is going to break apart into silver ion plus our chloride ion. And again, the Ksp here, in this case, they gave it to us 1.6 times 10 to the minus 10. We could write our Ksp expression for this. Again, products over reactants. So we're going to have our silver ion times our chloride ion. And again, here, our reactant side is a solid, so we would not include it. So because in this case, for sure, you are only given the K value, you need to do an ice table. So this is basically how they got to the bottom there. So let's see how they did that. Initially, we're going to do 0 for our silver chloride. Again, we're not even going to really put anything there because it's a solid, so we don't have to worry about it. But we are going to do 0 on this side for each of those. The change here, again, going to be minus x on the left-hand side, but we have everything that's a solid, so again, we're going to ignore it. So on the right-hand side, we would have plus x and plus x. Each of the coefficients here are 1, so we don't have to put any numbers in front of it, which means at equilibrium, we would have x and x. Again here, we're not going to touch this side because it's all solid, so we're not going to even worry about it or try to put numbers that we're going to use incorrectly when we do this problem. Now at this point, what's different than the previous problem is we're not given any of the equilibrium concentrations. So now we put this into our Ksp expression. And again, basically, this guy goes here, this guy goes here. That's going to give us x times x will equal our Ksp value of 1.6 times 10 to the minus 10. That's going to give us x squared equals 1.6 times 10 to the minus 10. We're going to take the square root of both sides, and that should give us the x value that we see there when we take the square root of 1.6 to the minus 10. Going to give us 1.3 times 10 to the minus 5. And if we follow our table in, this is what this guy's concentration technically would be at equilibrium. This is what this guy's concentration would be at equilibrium. You may ask yourself, how can we relate it to here? And the way you can relate it to here is the same way we talked about when we talked about concentrations. If you go backwards, this is a 1-to-1 relationship, which means if this guy's concentration is 1.3 times 10 to the minus 5, then the silver chloride's concentration would be 1.3 times 10 to the minus 5 molar. So because it's a 1-to-1 relationship, pretty much when you solve for x, in the case of Ksp, when you solve for that x, it essentially will mean the molar solubility. And that's what this refers to. When we solve for this number here for the whole thing in molarity, this is what is sometimes referred to as the molar solubility. Molar solubility because you solve for moles per liter. Okay. By the way, if we wanted something like solubility in grams per liter, you would take it and times it by the molar mass of that substance. The moles would cancel and you would get grams per liter, which is another very common unit of solubility, grams per liter. This is, again, a common unit. And again, you could get to that by taking the molar solubility and timesing it by the molar mass from the periodic table. Any questions on that calculation there, the ice table? And just to give you an idea what the solubility of this would be in grams per liter, if I take silver chloride, which is 107.9 for the silver, 35.45 for the chloride, is 143.35 is the molar mass, I times it by 1.3 to the minus 5. That means that basically if I take this number and multiply it by 143.4 grams per mole, that means you have this in terms of the solubility of silver chloride in water. You basically can dissolve 0.002 grams. So that's like 0.002 grams in 1,000 milliliters of water. That is a very, very, very small amount that will dissolve in 1,000 milliliters of water. Basically 0.002 grams is all you could get in this circumstance to get the silver chloride to dissolve. And that's why, technically speaking, when we think about the solubility rules, we typically think of silver chloride as being insoluble. But what this calculation actually does show you is, even though pretty much 100% almost of what you have in that solution is the silver chloride together, there is still a smidge that will actually be dissolved in that solution, a very, very, very small amount. And that's why it's still considered an equilibrium. And that's why typically when you look at Ksp problems and you look at Ksp values, they are typically very small. And they're typically very small because they're for things that are insoluble to begin with, which means a small value of K means when we reach equilibrium, we are mainly over here on the left-hand side, and we mainly have the solid still there. But a smidge of it will still break apart into ions, but as you can see here, it's a very, very, very small number. Any questions on that? Okay. So why don't you try this one here and see what you come up with? So this is an equilibrium. The equilibrium constant is, we'll use 54 in this case. We're going to say we initially started with H2 at 0.5 molar, I2 at 0.5 molar. And we want to know what is the equilibrium concentrations of everybody at equilibrium. So you do need to do an ice table. So why don't you give that a try and see what you come up with. Take a minute or two and we'll talk about it. Again, try to follow the ice table similar to what we did. The difference here is going to be you're going to actually have numbers and X's on both sides. So see what you come up with, and then we'll talk about it. Okay, so let us take a look here. So in this particular case, we're given the initial concentrations, and we're looking for the equilibrium concentrations of everybody. So a good place to start usually with these equilibrium type problems is the expression. So in this case, we're going to do our products, which is HI. And we do need to square it because of the coefficient. We're going to divide it by our H2 and our I2, just like we had in the previous problem. In this case, is going to equal 54. So we do need to do an ice table. So this ice table, we actually did have an initial concentration of H2. So we would put 0.5 here. We also had an initial concentration of I2. We'll also do 0.05 or 0.5. And we weren't given any information about HI. So in that case, if you're not given any information about HI, it is safe to assume that's going to be 0 initially. And also because we weren't given any information about HI, it is also safe to assume that this reaction is most likely heading in this direction. And again, that's going to be important for our change part. That means that we would expect the reactants to decrease. So here we're going to use our x, and we're going to use minus x. Again, the coefficient here is 1. We're going to use minus x for this guy as well. Again, the coefficient here is 1. And over here on the product side, it should be increasing. So we're going to use plus 2x in this particular case. The 2 because of the coefficient here. And at equilibrium, what that means is we're essentially just going to bring everybody down. 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table, how we set it up, or anything like that? So this one is slightly different than KSP. KSP ones are done similar to this, but the difference with KSP is you will always have just a solid on the reactant side. So here you do have some reactants that are not solid, so you do have to play with that. It's minus x on the reactant side, which I think is your question over here. On the reactant side, it's minus x, and that is because, whoops, come back. That's because the assumption is this reaction is heading from reactants to products. So in order for it to go from reactants to products, you have to actually use some products, right? Some reactants up, right? These guys have to come together to make our product. And when you're doing that, what that means is the reactant side, those concentrations should start to go down. While on the product side, because you're going to be making some products, the concentration of those guys should go up. And in an ice table, the way we represent something being kind of used up as in the process of the reaction happening is we use the minus. So that's why the reactant side, which should be decreasing, is represented by the minuses, while the product side is represented by the pluses because it should be increasing. So to answer your question about will it always be subtraction on the reaction side, I'm going to say yes with an asterisk. So probably 99% of the time, most problems that you'll see in this class for sure, even honestly, most problems that you'll see when you go to 1B as well, and when you do a lot of these ice tables, it probably will be subtraction on the left-hand side, the reactant side, and pluses on the product side. So, you know, probably if you kind of no-brain it and just kind of do it most of the time in this class, and for sure you'll be okay. When you get to 1B, you'll probably be okay in most of the calculations. But I will say, to be truthfully honest with you, 100% of the time, it will not always be perhaps subtraction on the left-hand side and addition on the right-hand side. It may actually be reversed, but we definitely don't get into any of that in this class. You may see a little bit of that again if you get into 1B or something like that. But for our purposes, and probably even in 1B, most of the time, you're probably safe to assume reactants are lowering and should be negative on that side and positive on the other side. And again, with that, the important part is to make sure that you incorporate in the coefficient as well, because that really does do the kind of mole-to-mole relationship in the stoichiometry of it. Other questions on that? So in this case, we have the K value. And at this point, what you typically do is you go into your expression that we wrote earlier, which is our K is the HI. And again, it's squared there, divided by the H2 and the I2. And we're going to put our equilibrium guys into there. So that's going to give us 2x squared divided by 0.5 minus x times 0.5 minus x. And that is going to equal our equilibrium constant value of 54. So basically what we did is we just took our equilibrium guys and we put it into the expression where they go. So again, the 2x represents the HI, the 0.5 minus x is the I2 and the H2, and put in here. So at this point, what we want to do is basically solve for x. And to solve for x, there's a couple of different ways you could do it, but for us, it's going to be pretty much a simple way-ish. You may recognize it, you may not recognize it, but this guy right here is actually a perfect square on both sides. So you could actually take the square root of both sides. And if you take the square root of both sides, you will get on top 2x. On the bottom, you'll get just one of those guys, 0.5 minus x. And what I always forget to do is actually square root the 54. So if you square root the 54, and you'll get something that looks like an answer, perhaps 7.348. So in this case, we're going to take the bottom and multiply it to the other side. And if we do that, that gives us 2x equals 3.674 minus 7.348x. And again, I took the entire bottom and multiplied it to the other side. We're going to combine our x's to the other side. So that's going to give us 7.348 plus 2, because we're going to add it to the other side. And that would give us 9.348x equals 3.674. We're going to divide both sides. So we're going to take our 3.74 and divide it by 9.348, going to give us an x value of 0.393 in this particular case. Any questions up until there? Now, you may think, oh, I did a lot of math, which just was not too bad math, actually, compared to some that you will see in 1B. What that x value is not really the answer per se. It is all the x values that we see in the table. So including the one over there, which I can't get to because I moved something in the way. There we go. Including this x value here. So to find the equilibrium concentrations of everybody, we basically would just plug our x value in. So we would take the H2, which from our table we see equals 0.5 minus x, which means that's 0.5 minus 0.393. And if we do that, 0.107. And since it's a concentration, we would put the molarity in there. We would do the same thing for our I2, which happens to come out exactly the same in this case, 0.5 minus x, 0.5 minus 0.393. And when we get to our HI, we can see from the table, it is 2 times x. So we would take 2 times 0.393. Gives us 0.786 molar. And what these would represent are the equilibrium concentrations of each of these guys once the system reaches equilibrium. Any questions on that? And what you could see is, right, if you look at the concentrations and you look at the K value that we have, The K value is 54, which is considered a large value, which means when we reach equilibrium, we should mainly have products, right? And if we look at the concentration of the equilibrium side, we have 0.786 molar versus 0.107 on each of the reactant side. So we do have, all that good stuff. The nice thing about sort of these calculations and when you take 1B is it's pretty much math. So if you're good at math, this is pretty much what you'll do in 1B all day. But the nice thing about math is you could kind of check your answer. So the way you can kind of check your answer to make sure you didn't mess up anywhere along the way in terms of the math is these are now the equilibrium concentrations of each of these guys. And if you take all three of these values and you stick them into this expression that we have up here, you should get pretty much 54. And you do get about 54 when you do that. Yeah, so in terms of checking yourself, you should be able to do that. It's a good way to do it when you do these type of problems. Now, in terms of, is this the way you solve all equilibrium problems? This is the way you solve all equilibrium problems when you're given only the initial concentrations. Now, if you were given the, for example, equilibrium concentrations of everybody, except for one, so I'll go back to that question, which was like this question here that we did earlier. In this question that we did earlier, they gave us the equilibrium concentrations of everybody except for one person. And in that case, you could just use the expression to solve for the missing sort of concentration because you already have the equilibrium concentrations of everybody. But when you're given only the initial concentrations and in like an equilibrium constant value, you do typically have to do ice tables and do this type of problem. Because ultimately, if you're looking for something at equilibrium in terms of their concentrations or even their pressures, you need to get the value at equilibrium, and that's not always going to be obviously the same as it is at initial. And you can see also if you compare the initial concentrations of H2 and I2 to the equilibrium concentrations of H2 and I2, we do see that it decreased, right? It went from 0.5 to 0.107, which is what we expected to happen. And we also see an increase in our products that started at 0 and ended up, in this case, at 0.786. So typically ice tables are the way that you solve them. Equilibrium problems when you're given initial concentrations and not equilibrium concentrations. Now, in terms of the math part of it, which is definitely outside of our class, but when you do get into 1B, Chem 1B and all that, and you do these problems pretty regularly, pretty much a majority of all the calculations are these ice table type problems. There's just some different variations on each of these problems that you have to watch out for that you'll learn when you take that class, if you take it. But they're all pretty much the same calculation, which is good. There are multiple ways you could solve this. So they do get a little bit more complicated. You may have to solve these guys using something like the quadratic formula, which again, for our class, you won't have to, obviously, when you do get to 1B. You also sometimes people solve these problems using a process known as successive approximation, which is a little bit more complicated and can take a little bit longer of a way to sort of solve it. So there's a lot of different ways to sort of solve these problems, and you sort of apply it depending on sort of the application. But for us in this class, since really, I'm not sure really why they make you do ice tables here at the end. Again, I think it's just sort of a preview of things to come, perhaps. Ours will be very, very sort of simple ones if you have to solve any. It'll be like the Ksp example we just did. It'll be like this example here, where it's not extremely difficult or anything like that. Okay, we're going to talk about the final and everything in just a second. And but first off, any questions on ice tables and how to do it? And again, ours will be sort of more basic sort of ice tables. I believe the post-lab questions for today's lab will have a couple of ice table problems, maybe, or at least one ice table problem that she has to kind of do to solve it. Any questions on any of that stuff here? I think that is it in terms of, in terms of that. So that is it in terms of the material. Congratulations. Yes, you've successfully almost completed Chem 3A. So a couple of things. Let's talk about the final. So first off, reminder, the final exam is 1 week from today, May 20th, and it will occur at 10:30 a.m. and you will take it online like you've been doing. But again, different than before, like we talked about last time, you will be required to log into Zoom while you're taking your final and have your camera enabled so I could, watch over and make sure everything's happening correctly. So that is a requirement. You are going to ask to have that done for the final exam. So you do have a week or so, or over a week, since we talked about it on Monday as well. Again, make sure you got that set up, that you can do that and log into Zoom and obviously have your camera enabled. So again, we can monitor what's happening here on the final. The exam technically is from 10:30 to 12:30, I believe. Again, you may get a little bit extra time, obviously, and stuff like that, but it will be within that. No card for the final or anything like that. So like our normal exam, you cannot use any type of notes or anything like that other than what it will be provided for you on the final exam. So it will be given pretty much, the same type of information that you're given on the previous exams. Again, any type of constant type value will probably be provided for you like normal. Any type of conversion factor like you were given before will be given to you as well. Obviously, a periodic table would be given to you. Things like specific heat capacities, heat effusions, those type of things would also be provided for you on the final as well. Things that you were supposed to know, sort of by heart for all the previous exams, you're still supposed to know by heart as well for the final exam. So again, you're still supposed to know, those polyatomic ions. You're still supposed to know the geometries and stuff like that for Lewis structures and all that kind of stuff. So you still need to kind of know all those kind of things. So anything that you need to know for sure for a previous exam, you still need to know. Now, in terms of the exam, I think it obviously is going to, when you think about maybe what to study, how to study, you could still, I think, access your old exams and stuff like that. So that's probably a good resource. In terms of the homework, I think I hit the right button. So they should be back available for you online if you want to kind of go back through and kind of use it for review. If it's not working right, let me know, but I think I did. So I'll double check, but I think you should be able to. I'll double check just in case something got accidentally clicked off. I'll double check and make sure that you can see exam 3. So just like normal, everything, you should know how to, balance equations for some compounds and acids. So, it's not going to be anything new. So anything that we learned along the way should still be the stuff that you still know how to do. Just give me a sec to read it all here. Yeah, I think you can use the same reviews that you used previously. Again, nothing's really different, except the only chapter that's not going to be on there, and maybe a review sheet would be this one here, which obviously we just did. But the exams, I think, covered through chapter 16, so pretty much all the reviews that you had previously should still be good. The truthful answer, Grace, is I haven't written yet. I still have a few more exams to go before our finals next week to write, including one tomorrow. But honestly, it will be usually the final will be similar to a regular exam in terms of length. There probably will be a few more questions, obviously. So a normal exam will be like 100 points. So again, I'm not going to promise for sure this will be what the point total will be, but maybe, you know, this exam will be 130 points, 150 points, something like that. You know, so there might be a little bit more points. And in terms of the questions, it will probably be, maybe it's a few more questions than a regular exam. So it's not going to be like, I don't think, tremendously longer than a normal exam. It's just going to be a little bit more obviously comprehensive than a normal exam. So it will cover, you know, all the chapters 1 through 17. The final will still be worth whatever it says on the syllabus. And again, I teach at 5 classes, so I don't remember, but 20% sounds about right. Technically speaking, we don't have class on Monday. But if you guys are interested in a review or something like that, I probably can. I'm trying to think. Probably could do one around our normal time if you want, or people interested in perhaps that. That way you can think about it over the weekend. If you have questions, you can maybe ask your questions and stuff like that. So if you want, we could do a review. Maybe how about just around our normal lecture time? That's probably good for most people, I'm assuming. So again, officially, you don't have to come. Obviously, officially, I think finals officially start tomorrow, if I'm not mistaken. So I think finals officially start tomorrow. So if you want on Monday, that way they'll give you some days to look over stuff and maybe think of some questions that you might want to ask. And we'll just hold a review at our normal time. So like 10:30. So I'll put the invitation up on Canvas like normal and stuff like that. So that way, if you have questions, obviously you're more than welcome to attend, and I'll try to answer your questions and stuff like that. Yeah, so everything will be done just like we've been doing. So you all log in, and everybody should start. Since it is a final, you need to start the final at 10:30. Everybody, 100% of everybody should be there at 10:30, like we were in person and taking the final together. And again, everybody will need to log into Zoom, and we'll have to have their camera on. So again, I can basically sit there and watch what's going on and all that kind of stuff. Again, that's what the department wants for the final for sure, to make sure that there is some sort of proctoring. And I think this is just going to be the sort of the easiest way to do that. So everybody should have some type of access to a camera that they can enable while they're taking it and to log into Zoom. And again, it would be just like you were taking in front of me. I would be sitting there and watching. In terms of exam 4, I'll be honest with you, I have 4 exams this week. So my goal is to try to get it graded by the end of this week, in the next day or two. And definitely by the weekend sometime, you definitely should see what you got on exam 4 and stuff like that. Yeah, in theory, you shouldn't use, just so we're all clear on this, since I will be observing, you shouldn't have really anything in front of you except for what you're writing on in terms of showing your work and your calculator. So I don't have any type of issues like that. Let me be very clear on that. Even the periodic table or anything like that, you should not have out. So make sure you use whatever is on the exam that's provided for you. Please, again, don't have any other sort of papers out other than what you're writing with and your calculator. Again, I don't want to see anything out or anything like that, so we don't have any issues with that. Yes, you do. So the final is going to start at 10:30, and that is when you should log into Zoom. And at that point, you could start taking your final. But you are required to start the final at 10:30 because it is the final. And that way, since there is going to be sort of manual proctoring going on, everybody does need to start the final at 10:30 on the nose. Doesn't be exactly on the nose, but you got to log into that, Zoom conference for the final at 10:30. And then again, any type of adjusted time period for those people that have those type of accommodations and stuff, obviously, just like normal, your time will be adjusted and you just continue working and all that. And everybody else will have the the normal sort of amount of time for the final, 2-ish hours or so, 2.5 hours, whatever it is. And, everything will just kind of behave like you've been taking the exam. The only difference is everybody does, in this case, need to start at 10:30, okay? Because technically speaking, it's the final. Technically speaking, that way we avoid any type of conflicts with any other finals that you might have or anything like that. So everybody needs to log in at 10:30. Everybody needs to start the exam about 10:30 as well. Let's see. Yeah, so I don't believe we're going to be doing any type of dropping of exams or finals or anything like that. Finals would be nice. Drop your 4 lowest exams and your worst final. That would be good. But you won't get to do that. But the things that will be dropped is the same stuff that was on the syllabus from the beginning. You'll get a drop, I believe, a couple of labs, your 2 lowest labs and your 2 lowest pre-labs. I think you'll also get a drop your lowest online homework as well. So you get to drop those things like normally that we did talk about. Other questions on that? Now, some of you did have questions in terms of the lab and checkout and stuff like that. So I actually did just get an email, I think the other day, yesterday, I think, in regards to checking off. So none of that stuff will be dropped. Truthfully, I don't drop anything or added any extra credit or anything like that until the very end, because it's just a pain to have to do it and then maybe has to redo it. So at the very end, I go through everything when I have to do the final grades, because it's just easier just to do it all at once. I'll drop all that stuff and, obviously add in some extra credit and all that kind of stuff to it. Now, in terms of the lab, a number of you did ask, I think, about it the other day and stuff like that. And like I said, I just got an email. So in terms of checkout, my understanding is you're all good. Obviously, you're not allowed on campus, so you cannot check out physically from it. You don't have to worry about checking out of your locker or anything like that. My understanding as well from the last email that I saw, I don't think anything's going to change, but I think from the last email that I saw, I'll answer your question in just 1 second when you just finished about the lab. In terms of the lab, my understanding is anything that you might have broke before we were off of campus and you technically would have been charged for as well. My understanding is they're just going to let all that go for this semester. So just to make everything a little bit easier for everybody and not have to worry about fines or anything like that. If you broke something along the way that you were technically responsible for, my understanding is you're good on that. You won't see any lab fines or anything like that in terms of the lab locker. And in terms of anything, if perhaps you realize that you had any type of personal item that was in your lab locker, I'm not sure what that would be, but if you think you have any type of personal item in your lab locker, what you should do is you should email me and then I'll give you the information as to what I need, and then you could email them, or I'll give you the information. Then you can email the stock room. And my understanding is, if you happen to have had anything personal in your lab locker, I don't think they're allowed on campus yet either. So when everybody's allowed on campus, they'll go to your locker and they'll take it out for you and hold it for you until you are able to perhaps get back onto campus and stuff like that. I don't think in terms of the lab coats or goggles, that's probably what they envision in terms of that. Because to be truthfully honest with you, you will be given a brand new one every time you're in person on campus. So every time you take the class, they'll provide you a new lab coat and goggles. So other than the lab coat and goggles, which obviously is in everybody's locker, I wouldn't worry about those because, again, if you come back to campus, they'll provide you with a new lab coat and goggles. But for some reason, if you had, I don't know, a pair of shoes in there, glasses, I don't know, whatever, maybe more of a personal item outside of lab coats and goggles, just contact me and I'll give you the information as to who you need to email in the stock room. And like I said, if it happens to be, again, some type of personal item outside of lab coat and goggles, let me know, and then I'll give you that information. You can contact them. And like I said, they'll hold it for you until everybody's allowed, maybe perhaps back on campus, and then you could get it and all that kind of stuff at that point. Okay, so that should be lab. Any questions on lab while I read some of these questions here? That is correct. So I think the easiest way for this one, there is that Proctorial app. I think the easiest way, just because, you know, we haven't really used it, would be to log in through Zoom and again, have your camera on so I could watch you sort of taking the final like I would if we were in person. And it'd be just like you're logging into this normal sort of lecture, except that, hey, if you want to put your camera on, you throw your camera on, but you will have to put the camera on, obviously, for the final. So we normally keep it off and everything like that, but you will have to put it on. You get to see everybody again. That would be good. That'd be nice, right? And you will just have your camera on so I could obviously watch you taking the final, and then obviously you'll take the final like normal. At this point, I think the final will still be the same sort of version or type of exam where you'll just have that on, and then you kind of open up your Canvas screen, obviously, and go take it through there. But I still need to be able to obviously visually see you taking the final, and that's what the department wants, to sort of make sure everything is, you know, on the up and up for the final for sure. Any questions on anything else in terms of that? Or what's going on? Okay, so just to review here, what we've decided is we will have a review session on Monday. And we will do it on our normal lecture time, which is 10:30. So that Monday is what, the 18th, right? 5/18. And again, we will just log in like we do lecture and stuff like that, and you could ask questions and all that good stuff. And then again, the final exam is May 20th. Again, a reminder, everybody needs to start it at 10:30 for sure, okay? And again, it's the final, so everything is more sort of rigid for that. And again, that'll avoid any type of conflicts that anybody should not have in that case. And again, you need to have a camera enabled so we could see you taking the final and all that good stuff. Any questions on any of that stuff that's happening? Now, in terms of lab, we do still have one more lab to go, which is the Le Chatelier's principle. So as soon as we're done here, I will post that up. And like normal, we'll take a little break. And it's a good question. We'll do cameras, and we'll see about the mics. I'll let you know. But definitely the camera needs to be enabled. I need to be able to see. And probably your mics as well, just to make sure nobody's yelling out answers to you around the corner or something like that, I suppose. So for sure, the video, I'll let you know on the mics, but probably anticipate both of those things being sort of open as well, again, so I could sort of hear what's going on and see what's going on that's happening on the final. Other questions on that? Okay, so the Le Chatelier's principle is coming up. So it's basically a bunch of reactions that were done. They added things to these reactions that are at equilibrium. You're going to see if they shifted to the left, shifted to the right as well. So I'll let you know about the mic and stuff like that. You can, we'll see, but definitely the video does need to be on. Yeah. All right. Other questions? I'll think about a way we can maybe do that. We'll see. But definitely the video needs to be on, and we'll figure out the mic as well. All right, any other questions? Okay, so again, a reminder, you got the Le Chatelier's. I'll be up in a few minutes. Again, if you have questions on that, you can come to the lab. I'll be there. And I'd just like to say that congratulations. Yes, you've completed, well, almost completed, except for that final, I suppose. Just Chem 3. Should be very proud of yourselves. I enjoyed having all of you in the class. I will say, out of all my classes, were the best here in terms of continuing attendance, participation, and everything like that. So with the situation that occurred, you should be very proud of yourself for sticking with it and obviously coming here to the end. And, you know, I wish you the best of luck on not only our final, but all the finals that you're taking. And like normal, if you do have any questions over the weekend and stuff like that, feel free to email me. And, you know, I'll be more than happy to answer your questions. Again, we'll do a review on Monday at our normal time. And like I said, the lab will be up in a few minutes here as soon as we're done here. Okay. All right, guys, I'll see you in lab if you have questions. Otherwise, make sure you do get this one turned in tonight before 5, I think is when it's going to be due. And a reminder that, what I was going to say here, got that. I think that should do it. And a reminder, I will try to get those exam 4 grades as soon as I can, okay? So that you're kind of on the first on the list there when I get a chance to start grading. So hopefully by the weekend, sometime this weekend, and you should be able to see what you did on that. All right, I'll see everybody in a bit. We're taking maybe lab will start maybe about 12:10. I'm gonna go make the lab available to you. And again, if you have questions, please come by.